Welcome back to the series on how to begin data analysis. There has been a long gap for this video to be uploaded. In the earlier video, we had covered hypothesis testing for quantitative data, qualitative data, unpaired setting. So in this setting, I cover qualitative data in a paired data setting. Let us see. So, as you have already been familiar with this flow chart that on statistical methods, so we have estimation on one hand and the testing of hypothesis on the other. So now presently we are dealing with qualitative data analysis. In the qualitative data analysis, so there are two kinds of data formats are there: unpaired data and paired data. So regarding unpaired data, how to calculate chi-square and the information about Fisher's exact are already been given. Now I talk about paired data, in which we we are going to talk about McNemar test or McNemar chi-square test and Kappa statistics. So if you see in the earlier video, we had covered a 2 by 2 table of this setting. This kind of setting, this is relating the risk factor. So this kind of data is called independent data or unpaired data. So in this, the individuals are different. So as compared to this, we paired data setting. So this is an example in which uh, a group of individuals are measured twice at first time point or second time point in the first sample taken and the second sample taken on the same individuals. So this kind of data is required to be tabulated in a different manner other than the independent data that we did disease versus factor association. Now in this, first sample positive, first sample negative, second sample positive and second sample negative. So both samples are positive and both samples are negative. One sample is one sample is positive and the second sample is negative. And first sample is negative and the second sample is positive. These two are discordant cells, and the analysis of this kind of data depends on these two cells. So for this we use McNemar test. The McNemar test or McNemar chi-square test is based on 2 by 2 classification table. So we had already seen that in a two-way table, the simplest form is 2 by 2 table. Uh, so the studies in which the patients serve as their own control. So first sample, the same individuals, second sample is also taken. So it is like before and after design. Uh, So consider a hypothetical example of 900 school children. They were questioned present or absent of symptoms uh, of severe cold in two seasons, in two consecutive years. So, uh, so year one and year two. So whether they had severe cold symptoms, whether there is any change in the pattern. So in season one, so you will see in the example, out of 243 children reported to have severe cold, 228 had no symptoms. So this is one discordant pair that 93% they had the in season one they had these many uh, were having had no symptoms in the second, whereas in the second, out of 257, so when we looked at only 300 had with no symptoms, only 300 had symptoms in the season 1. uh, Let us look into table. So basically, what we do in the McNemar test is we formulate the null hypothesis. The null hypothesis is based on the discordant cells. So the probability of the cell B and probability of cell C are are the same. In the simplified terms, none of the two seasons the absence of symptoms differ from the other. Thus, the alternative hypothesis is that the frequency of presence or absence of symptoms in the two seasons are not equal. Here, the test chi-square of McNemar test is based on these two cells, B minus C modulus ignore sign minus 1 whole square divided by B plus C. So it is clearly as shown on substitution of these two values in this, and we got a McNemar chi-square value as 9.5. And the calculated value of McNemar chi-square value of 9.5 is more than the threshold value, critical value of 6.67 at 1 degree of freedom. So the null hypothesis is rejected. Conclusion is that, and it is written as p less than 0.01. In other words, the frequency of presence or absence of symptoms in two seasons are not equal. So the other test is Kappa statistics. This is used for the extent of agreement in this is intra inter inter observer agreement, and this is also a paired setup. If you then suppose a hypothetical example where two pathologists gave their diagnosis on a group of slides, histology slides. We give an example here on cervical biopsies in the detection of precancers, that is cervical intraepithelial neoplasia of grade 1 plus. So this here, the example here is cross tabulation of readings by two pathologists. Pathologist one is taken here and readings of pathologists on the same group of slides. So here if you see, pathologist says both pathologists agree that the lesion is present in 39 and lesion is absent in 102. So these two are discordant. When pathologists when pathologist 1 says that lesion is present in 46 of them, the pathologist said the lesion is absent. Similarly, this 9 is also a discordant pair. And let us look at how to compute the extent of agreement in between two pathologies. We see that using the cells A, B, C, D. So we based on these cell values, we calculate the expected cell value. Expected cell value is 0.53. Observed agreement is observed proportion is. So using these two, we calculate the Kappa statistics. It is called Cohen's Kappa by the name of the inventor. So we substitute here, we'll get 0.38 is the Kappa. So there are guidelines for interpretation, different guidelines by different authors. So the value of Kappa less than 0.2 is a poor agreement. The value between 0.21 and 0.4 is fair agreement, and 0.4 to 0.6 is a moderate agreement, and 0.8 to and you see, and 0.8 to 1 is got very good strength of agreement respectively. So the value of kappa in the present example is 0.38, indicates that the agreement adjusted for that expected by chance. So this is interpreted based on the magnitude of kappa. So the agreement between pathologists in the detection of lesions is just fair. With this, thank you. See you again. Easy by